Hello, what's up, what's up? Hope you're doing well. Welcome back. We are writing an operating system from scratch, working on the second stage of our bootloader. Last time we've worked on creating a physical memory maps or physical memory pages allocator. And today we are going to get acquainted with the world of file systems. Let's get to it. First things first, let's address an issue that's been bugging me for a bit now. And that is the fact that we have actually made a little bit of a mistake when we defined our script here that created the disk image. And the issue will become apparent if we go to a new shell and do fdisk dist and disk.image. So here we can see that we are welcomed with this message here. The primary GPT table is corrupt, but the backup appears okay, so that will be used. So basically we did something that corrupted the GPT table, the primary one. So let's figure out what we did wrong. So here, if we take a quick look at how we've created this disk image, we basically create a new, so G means, so these are the parameters that we fed to fdisk. G means new GPT partition table. NP is for new partition. It takes a partition number, which is 1, and it takes a first sector and a size. So here, the first sector, that was basically the minimum that fdisk could take, was basically 2K, and there are reasons for that. fdisk will try to push for
sectors
that are aligned and stuff like that to a sector size boundary, but and it's very conservative in doing so. So basically, the minimum sector it is allowing us to allocate for our partition is this 2K here. Except that when we loaded our disk image on the loopback device, we've basically told it that our partition starts at sector 1. And this might be the issue, because here what we've did is we've basically overwritten the partitions that fdisk created, or the primary ones, because for GPT partitions, there are 2 partitions, one that's at the beginning of the disk and one that's at the backup basically is at the end of the disk. So that's why we get the error message when we try to open our GPT or our disk image with fdisk. We get told that the primary GPT table is corrupt. So that is the reason. So let's fix that first. So here what we want to do is we want to basically take 2K sectors, or the size of 2K sectors, and put it in here. And so let's do that quite fast. So I'll do that. 2048 times 512. And let's copy that. There we go. Yeah, so that's the size of the start. Basically, that's the offset of our start sector for our partition. And that's where we want to create our first F16 or FAT16 partition. Right, so with that done, you can just save that, and we can take a look at how the disk looks before and after that change. So let's do that. So I'll use XSD for that. I'll give it a seek of 0 and a length of, let's just take 4 sectors. Yeah, should probably do something like this. And should tell it to group them in 8 or in 4s. And we just give it the disk file. Right. So let's try to see what we have here. So at the very beginning of the disk, we have our stage 1 bootloader. We can recognize that by just looking at the strings that we have in here. These are the error messages that we've put into our bootloader. And if we look at the second sector here, we can see that we have a EFE system FAT16 partition that's written here. Whereas here we'd probably expect the GPT table. And or basically the primary GPT table. And here's how that's how that works. So here we know that from the GPT or GUID partition table scheme, we know that at LBA1, which is our first sector, or sector 2 if we index starting 1, we have our primary GPT table header, which is the one that was corrupt. And here at the very end of the disk image, we have our, so basically at LBA -1, which is basically the very last sector, we have our secondary GPT header, which wasn't corrupt in our case, and this one was. So right after our first sector that has our first stage bootloader, we want to have our GPT header. Okay, so let's rerun our build to generate a new disk image. Okay, so let's take a look at our new disk image with XSD. Right, so here we see that the second sector has changed, and that we actually now have what looks like a GPT header. So let's make sure of that. We should probably just do this. Yeah, that looks better. So here we have EFI part. If we go here and take a look at what the GPT or GPT header looks like, you can see that at offset 0 we have 8 bytes, which are the signature, should contain EFI part as a string. Then we have the next 4 bytes that are the revision number, should be so 0100. So let's go back and see. And yeah, we do have 0100, and then we have, so let's go back here. Then we should have 4 bytes at offset 12, which are the header size, and usually these are 5C0000. And then we have 4 bytes of CRC, and then we have at offset 20, we have 4 bytes which are zeroed, and then we have 8 bytes which are the current LBA. This for us should be 2, I believe. Then we have the backup LBA. This should be the sector for the backup GPT table. And here, the things that we are interested in are basically the list of partitions. So here is the first LBA for partitions and the last one. So we are going to be interested in reading these partition entries. Or rather, these are the actual partitions. Basically, this is the portion of the disk that is actually usable from a partition table standpoint. And here we have the starting LBA of the array of partition entries. And this is usually 2. So basically on the LBA number 2, we will get the partition entries. And here we have, of course, the number of the entries in that array. And of course, the size of every entry, which is basically fixed to 128. And partition entries look something like this. So we have 16 bytes for the partition type GUID, and then we have 16 bytes for some unique ID. And here we have 8 bytes for the first LBA, so basically where this partition starts on the disk, and 8 bytes for the last LBA, or where this partition ends. Of course, this is inclusive. And here we have 8 bytes for attribute flags, and we have 72 bytes for some optional partition name. I don't think all partitions have names. It's optional, I think, but we'll see. So let's go back to our XSD here, and let's try to find those things. So here we have 16 bytes, which are the signature. Then we have so signature, and this is the revision or the version. I don't remember what they called it. This should be the size of this entry here. This should be the checksum. This should be reserved. This should be the number, or rather the start LBA. So this whole thing here. And, or rather, no, this is the current GPT header LBA. So we are at LBA 1, that's correct. And this one here would be the, this one here would be the last GPT header, or the LBA of the backup. This one here would be the first usable LBA, and this is 0x800. So this is little Indian, so 08 and 00, so 0x800, which is 2K, 2048. And this, so this whole thing is that. This whole thing is the very last usable LBA. And here we should have some sort of ID or something. Yep, that's the disk GUID. This here would be the LBA for the partitions, partition list. And then we have here the number of partitions and their size. If I remember correctly. Yeah, that's right. So the number of partitions and their size, and then the very last 4 bytes, this one here, is the CRC of the partitions. And of course, we pad this GPT header to the next, to fill the current sector, basically. So here at the other sector, just remember that a sector is 512 bytes, which is 0x200 in hex. So if we want to go one sector from any address, we just add 200. So here we are at 0x200, which means that this is the first sector. And if you want to go to the next one, we just add 200, which gives us 0x400. So we land here. Okay, so 400 is the LBA2. Basically, this is where our partition table starts, and here we can basically look at the partition format through this. So the first 16 bytes, this whole thing here, would be the partition type GUID. Oh, my bad. So these 16 bytes, so the full line here would be the partition type GUID. Then the next 16 bytes are the unique partition ID. Okay. Then here on the third row, we have 0800, which is the first LBA for this partition. And remember that 0x800 is basically 2K. That's where we've started our FAT16 partition. And here we have 16, or rather 8 bytes for our flags. We'll get to the flags in a bit, but for now, we don't really care about those. And we basically fill 72 bytes here with some partition name, but we don't have a partition name, so they're all zeros. So that's good. So now if we want to go to our first partition, we need to go to this address here. So 0x800. So let's do that. And to do that, we just need basically to take our XSD and just seek. So let's do it this way. And we want to do 0x800 times sector size. That should be good, I think. So let's see what we have. And of course, you can see that we actually find our first partition, that's FAT16 partition. And what we are going to do in a few minutes is we are going to basically do this same process, but with C code. We first are going to read a GPT table header, and then we are going to extract the partitions list from it, and we are going to go from partition to partition until we find one that we can read our kernel from. And once we do that, then we are going to load that partition and see how we can interact with it. Before we start working on the code, I want to address the first hurdle of confusion that happens when first getting acquainted to the concepts of partition tables and file systems. So a partition table in a nutshell is a collection of partitions. That's basically it. And its function is it splits the disk into logical regions that are basically independent from each other and can be treated as so. So if the disk is a collection of sectors, then the partition can be seen as a subset collection of those sectors that are on the disk. I don't know if there is a requirement that partitions would have just contiguous sectors, but I think it's always the case, at least in all the partitioning systems that I know of. So let's take an example of what a partition table would look like. And here we're looking at the GWT partition table, or GPT for short. This is very simplified. We'll get to the details in a bit. But here we have a GPT header that basically has a field that tells us where the partitions lists are. And if we follow that field, we basically land on a sort of array of partition entries. And that array basically tells us that partition 1 starts at sector 100 and ends at sector 400. It also tells us other info like the type of the partition, stuff like that. But this is very much what a partition table is for, just a list of the partitions on the disk and where they start, where they end. File systems, on the other hand, describe how files are structured within a partition, or how files are laid out on disk within that partition. It basically, I guess a simple way to look at it is to say that it basically maps a file path to the file on disk, because if we don't have the file system, we will not be able to find a file on disk unless we actually know the content of the file and we scan the disk for the content of the files. In practice, it's a bit more convoluted than that, but we'll get to that. So an example of a file system would be something like ext2, ext3, ext4, and the file allocation table. So file allocation table is FAT for short, and that's where FAT12, FAT16, FAT32 comes from. So just in a nutshell, what the FAT file system does for us is we have a fat header that basically has a field that says this is where our root directory starts from. Basically, this is the root of our file system. We follow that root directory to find a list of entries, and entries can have a type. They can be files, they can be directories, stuff like that. And for every file on that entry, even directories are considered files, we have the address of its first cluster. So that's how we are going to know where to look for the file on disk. So we find that first cluster, we load it from disk, and we'll get to what a cluster is in detail. But just know that a cluster is a collection of sectors. And then we, so in file allocation table, the files can be fragmented on multiple clusters. So if you've used a computer any time within the 2000s, you might have heard of defrag, stuff like that, especially if you're using Windows. So that's where the need for defragmentation comes from. Files can be fragmented, and it means that we have the first cluster here. So if we take this example, file 3, we know that its first cluster is 4. We go to the cluster table and we load cluster 4, of course, from disk. Then we want to see where the next chunk of that file is located at. Then we go here to the cluster table. On cluster 4, or entry number 4, we can see that next is 5. This tells us that basically we need to read cluster number 5 to find the next chunk. So we go to disk and read the cluster number 5. Then we come back here, go to 5, and we can see that next is 9. So you can see that the clusters are not contiguous. So here we need to skip all the way to cluster 9 on disk, read that to memory, and then we go back to the cluster table, look at entry number 9. Here we are getting told that next would be 12. So we go read 12 from disk, we come back here, and at 12 we get told that next is FFFF, and basically that means that we have finished loading the file from disk. And this is how the cluster table would look like without fragmentation. We can see that here for this same file here, we read cluster 4, then cluster 4 sends us to cluster 5, which is basically adjacent to it. Then cluster 5 sends us to cluster 6, 6 sends us to 7, and 7 is the end. So we read the file faster. So that's why the file allocation file system didn't really do well, didn't age that well, because it had a lot of issues with fragmentation and running around chasing clusters on disk. Yeah. Right. Let's start by creating a new file that I'll call fs.h for now, and probably add a new one, fs.c. And if we go here, fs.h, we do the header guard. So call this file system. So just define it. There we go. And here I will basically create the GPT header struct. So let's type def struct, and I'll call this GPT header. And in this struct, we will have 8 bytes for the signature. So I'll just do u8 signature, and we know that we have 8 of those. Of course, here I'll need to import. So include types.h. There we go. And here, let's put in a revision number, which would be 4 bytes. So this would be a utility2 revision. And then a header size. So 4 bytes for that. Header, probably should just call it size. There you go. Then we have 4 bytes of CRC. So it's just CRC. And then we'll have 4 bytes reserved. Something like this. And then we have, just do something like this. There we go. And then we have, so 8 bytes or a U64, which is the current LBA. Then a U64, which is the backup LBA. And then we'll have a U64, which is the first usable LBA for partitions. So first usable LBA. And of course, we'll have the last usable LBA. And then we'll have 16 bytes for the disk GUID. So we'll just treat that as cars, I guess. So disk GUID, and here we'll have 16 of those. And then we'll have a U64, an 8-byte int, which is the starting LBA for the partition entries. So partition entries start. And we'll have a U64, or rather just a U32, partition entries count. And then we'll have a U32, which would be the partition entry size. And then we'll have the CRC of the partition entries as a U32. So partition entries CRC. And then we'll have so zeros until the end of the block. So we can either add those here or we can just ignore them. So what should we do? We should probably just add them, probably. Right, so here let's just call this reserved true, and here we'll have 420 of those. So if we add up the sizes of all this, we should be at 92, which is basically the size of the header. So if we take one block size, which is 512, and we remove 92 from it, we get 520. So that's the size of this reserved here. Right, so now we have our GPT header. So let's go to our fs.c and start by include fs.h. Right, so here we'll create a function that I'll call, so hold on, I just need to go back to main and see what we did. So we have this convention here where we do the name of the module underscore init. So we'll keep that. So this will be fs underscore init. And of course, we probably need to declare it somewhere here. yeah, let's just put it here. So fs_init, there we go. And in this fs_init, first thing we will do is we will call a function that will load the GPT, the page table. So let's do that. We will do load GPT. And we should probably also just declare here GPT header and call it GPT or something like that. Oops, these were meant to be underscores. There we go. Just add in header there. So we will load the GPT into this variable with this function here. So let's write that function there. So load GPT. Right. So what we need to do here is we need to read from disk, but we need to read from disk into some memory. So I guess the first thing we need to do is to actually allocate some memory to read into. So let's do that. So first thing we'll do is we'll do GPT header pointer, call it GPT, and this will be a GPT header pointer conversion to PM alloc, and of course here we'll need to go ahead and import, so include, we call it PMM, okay. So if we go here, we need to give it a size and a type. So for the size, we know that the GPT header is, well, basically we know the size of a GPT header, so we just need to we need a size of GPT header. And for the type, we will probably just say that it's reclaimable, so that we can, because this is not something that we need to keep around once we finish the bootloading, so we can reclaim this part of memory. Right, so here we have, so what will happen here, as we've seen when we wrote this physical memory allocator, this will round up the GB size into a full page. So here what we'll be getting is an actual page of memory. You can see here that the size is 512, but it will get rounded up to 4096. So there might be some optimization to be done here where we can reuse this same page and load multiple things into it. But for now, let's just keep going and we'll see if we need to come back and do optimizations. Right, so here we have a page that we can read stuff into. So I guess the first thing to do is to read from disk. So that's what we need to do now. So let's call it BIOS read sectors. And the way this is going to work, we are going to pass it a start sector. So in this case, we know that our GPT is in sector 1. We are going to pass it a destination, which would be our GPT. And then we are going to pass it a count of sectors to read. And here we just pass it 1 for that. So here we don't really have this defined anywhere. So let's do something about that. Let's go ahead and do, let's create a new file, call it or let's just define it into, I don't really want to define it in fs.h. So yeah, let's create a new file, call it assembly helper, something like this, .h. Yeah, probably should sm helper.h. If I can type today. Hold on, did I actually change the name? Yeah, okay, fine. Right, so, and here in this assembly helper, we should probably just go ahead and do the same thing. Do the, so if not def, asm helper, define asm helper, and if, there we go. And here we are going to define that function. Should be void. This would be BIOS read sectors. And the things it takes is a U32 start sector, and then it takes a some pointer to somewhere, so destination, and it takes a U32 count, which is the number of sectors we are going to read into destination. So yeah, I guess we need to include types, and that should be fine. Actually, just one thing here. I want to avoid having any issues with C to assembly conversions. I will just tell the compiler that this should be a U32, and we'll do the we'll basically force the conversion ourselves. So yeah. Right, so here we should probably just include, what did we call that? ASM helper.h, and that should be fine, except this. And this, we will tell it that it's fine. We can convert that to U32. Right, now what we need to do is go ahead and implement this thing here. The way we are going to do that is we are going to create a, so create a new file, call that assembly helper.asm. And here what we are going to do is we are going to basically write actual assembly code for the ELF format. So we need to tell it that this format should be ELF, that we have a section that's called text, and that's executable. And in this section text, we are going to declare BIOS read sectors. Did we call it sectors or sector? Sectors, okay. Right. So once this is defined, now we can just go ahead and basically define the function. And this function here will basically do just the glue between the C code and the actual BIOS code that we are going to call. So what we are going to do here is basically just do the classic. So we are going to store EBP. We are going to create ourselves a new stack frame here. Then we are going to store the registers that shouldn't be clobbered by this, ECX and EBX. So here we will put in EAX So let's just do something like d word, and here we'll take EBP plus 8, just put it in hex 0x8, and this would put basically the star sector into EAX. And then here we will move into EDI, d word, EBP plus 12. 12 is C in hex. And this is basically our destination. And then we will put into, let's say, ECX, d word, EBP plus 16, and 16 is 10 in hex. So, yeah. And we can probably just do something like this, just to align them nicely. Right, and then what we need to do is we need to get the address of the function, the bias function we want to call. Or actually, rather than saying bias function, we should probably have some function in basically 16-bit assembly that then calls into the bias function. So here we need to get something, and we will just call into that something, basically call into that address. And once this is done, basically we need to move. So we need to reverse all our actions. So we will pop EBX. Then we will pop ECX. So basically we're doing the pops in the reverse order that we did the pushes. Then EDI, so that unclubbers our registers. And then we need to move, so we move into ESP EBP, right? To basically close the current stack frame and unallocate any local variables that we might have allocated on that frame, on that stack frame. And then we pop EBP, and then we return. So this is basically how any function is written in assembly. We have the prologue here that creates a stack frame, and here we have the basically the ending that reverses the creation of that stack frame and then returns to the caller. And if we wanted to pass some sort of return value, we can just do something like basically return values in the C ABI are always passed in EAX. So if we wanted to return 1, we can just move it into EAX, and the caller will receive 1 in its return value. But for now, we are not returning anything, so we can just go ahead and keep it like this. So here, remember that we have this, so this will not compile. So we need to figure this out and come back and fix it. Right, so now let's create this function that we are going to call into. And the way we are going to do this is in, I think putting in star.asm would be, I guess, the best way we can do this, because in this function here, we can access all our helpers that we've created to basically jump from project mode into real mode and back. And we will need those because we will need to drop into real mode to call into the BIOS functions. And then we need to come back into project mode to resume the execution of our bootloader. So let's put it in here. And we'll call it something like, so what's a good name? Protected read sectors. I don't know. Right. So here, so this is still a function in 32-bit mode. So we know that here we are in protected mode. So and in 32-bit mode also. So we need to basically do the same dance again. So let's save EBP here. We'll need a stack, I think. Let's do the same move into EBP, ESP. And then, so do we have registers that we don't want to clobber? I think we do. At least the registers that we use to send. So basically this will be called from our helper here. And we know that we've put EAX would be the start sector, EDI would be the destination, and ECX would be the count, the number of sectors that we want to read. So yeah, at least these should be preserved in case we need them in our other function. So let's just add a little comment here and do read sectors. Let's do EAX is the start sector. Then EDI is the test address. And what we say, ECX was the sectors count, something like this. Right, so let's at least save those registers. So push EAX, push EDI, push ECX, and we probably also need to save EBX since we have our address in it. So let's push EBX. Should probably just yeah, let's just reorder this a tiny bit just so that we know what we're doing. And here we will add any other register that we are going to use inside our function to basically not clobber them. But for now, let's just do the opposite, I guess. Let's pop EDI, then pop ECX, pop EBX, and then pop EAX. And here, of course, we need to move, basically move into ESP, EBP, and then we pop EBP, and we ret. Basically, it's the exact same thing that we did here, but we did it also over here. So here's the game plan for this function, or at least this is what I'm thinking would work. So first, we are going to create the LBA packet. So basically, same way we did in stage 1 of the bootloader. So we will actually go ahead and copy paste a lot of code, which is always great. Right, then we are going to drop into real mode, call the BIOS disk service or int, let's call it service. Then we, thinking about this, I think we will have an issue here. So when we are in real mode, we can only address the top 1 megabyte, right, of memory, because we are limited to basically what the real mode can access memory-wise. So if the destination address that we want to write things to is not in that first megabyte, that means that we will need to basically trampoline ourselves by using some sort of temporary buffer that would be in the top 1 megabyte. And then we can copy from that temp buffer into our destination address afterwards. So let's write that. If this address is above 1 megabyte, use some temp buffer, and probably maybe use temp buffer always. That would save us from doing the check, and it would just streamline the execution. Needs to be seen, and here, of course, we call the BIOS disk, and we basically go back to protected mode. Then we need to, if we used a temp buffer, like this, then copy memory to this address. And then we return, or basically we have already set up the return, so we don't need to think about that. But these would be the things we need to do to get this working, basically. So dropping into real mode, we will use our, so let's try to find where we've created that. So we've created this set real mode here, and we have also this set protected mode here, which is really good. So let's just go ahead and replace those. So this would be set real mode, and go back to protected mode would be set prot mode. Is that what we called it? Set prot mode. Okay. Oh yeah, and we need to probably call into those. So let's call into those and see what we get. Didn't we actually create macros for these? I thought we have created macros for these. Okay, maybe in macro.inc. Oh, yeah, we created macros, go real and go prot, so we can use those. That would make it much easier. Right, so where we should be somewhere here. So let's just change this to go real and change this line to go prot, I think. Yep, go prot. Cool. So this step and this step are fine now. So we just need to do this. So let's create the LBA packet. And for this, I think we will need to go to our first stage and just get our LBA packet from there. So let's just copy that. Should probably also take this whole thing with us. Yeah, just copy that from there. And we should probably go ahead and define it somewhere. Yeah, you know what? I'll do this cleanly. I'll define the packet here in structs. Go all the way down here and do something like LBA packet. Something like this. Right, and probably just do. There we go. And this here. So let me just see where we've created that. Yeah, we did not create it here. So let me just, yeah, just remove this from here. We actually have this already. So let's go back to start.asm, and we should probably also just create the LBA packet somewhere here. So LBA packet, and we'll give it some address. What would be a good address for this? Let's just put it at C000. And now what we need to do is we need to basically go ahead and fill it. And I'll just put it up in here so we can see what we are doing. Right, so here in our LBA packet, we need the size first. I guess the size is always constant. So let's just move into, so size is a word. So word, this would be LBA packet dot size. And we just put into that. So the size would be 16, pretty much always. And then we have, so the count, so move word into LBA count, LBA packet dot count. And this here would be, so what is the count? I actually forget what the count is. I think the count is the number of sectors to transfer, and that would be ECX in our case. Well, actually, not ECX, just CX, since it's a word. Okay, so move. Okay, you know what? Probably need to reflect that on our definition of this function here. So we want just a word, so this would be a U16. That should be fine. And that means that if we go here, I guess we could still treat it as a double word here. It doesn't really matter. It doesn't change much. But yeah, at least we now know that we are going to have the correct size. We cannot pass a bad value from C side. So that's fine. Right, so here we are also going to move, so I guess the offset would be, yeah, so offset and segment would be where we are reading our buffer to. So here what we need to do is we need to probably either do the check, so either do a check here and write into some temporary buffer, or we can always use the same temporary buffer and have that as a basically fixed value here. I think the easiest thing to do is to always go through a temp buffer. So let's do that. So LBA packet dot so offset packet dot offset. This would be some sort of let's call it LBA buffer, and we'll try to define it afterwards. And then the segment would be 0. We don't really care about that. But the next thing we care about is actually LBA packet dot sector 0. This will be the actual sector that we are starting the read from. So here it's a word, so we can just go ahead and actually what we can do is we can probably just go ahead here and do this and this, and we can get rid of these two. And this way, sector 0 would be a double word, and sector 1 would be a double word for a total of 8 bytes. So that would be fine. So here in sector 0, we can just go ahead and write what's our count. Our count is ECX. And so let me just add a small to-do here. To-do, check that ECX is not 0. That count is not 0. Because if we are asked to read 0, we should probably just return immediately, or at least default to something sane, like at least one sector, or at least one page of sector, since we are actually getting past a page. But yeah, for now, let's just ignore it and see. And actually, we can also simplify something else. Now that I look at this, we can take offset and segments that are just words and make them one whole thing, and probably just rename this into something like address. Right, if we go back here, we can change this to address. I think we can do something better with this LBA packet. So let's do this. So this would be LBA buffer at 0x C000, and we will go all the way down here, probably just before this, probably just after this. And here we can just define something like LBA packet with, I guess, sub labels. And this one, oops. So this one would be size, and this one would be a word. And we can actually initialize the values here. So let's write 16, it's fine. Here we'd have the count. This one here is a word also. And we can actually initialize the count to something insane like 8, because 8 sectors is, so let's write it here, 8 sectors is 1 page, basically. So 8 times 512 is 4096. Right, so here we have the count, we have the address, and that would be a double. We can initialize that to temp buffer. No, what did we call it? LBA buffer, I think. Yeah, that should be fine. And here we can have, so sector 0, and this would be a double also, and this can be initialized to some value, we don't really care. And sector 1 is a double, which can also be set to 0. And with this, the LBA packet is actually part of this binary file that we are going to generate here, and we don't need to allocate it on memory. So we can just go ahead and remove this from here, and we can just close that. Right, and with this, I think we can just also get rid of that, because we've already created the size, we've already initialized the size when we've created the LBA packet. And we, so here, CX, LBA buffer, this can also be removed, because we are already doing it. Oh, and this is bad. Why didn't we put ECX in here? This should be EAX. Yeah, okay. Good thing we caught that. And this to do is actually has to do with this line here. Right, so we drop into real mode, and here we can just remove this, since we always need to read into a temporary buffer. And here we need to call the BIOS service. So let's do the classic. So here we can do the classic. So what we need to do is we need to put into DL the ID of the drive that we are to read from. For us, this would be our boot drive. So we need to find the ID and store it somewhere. Let's say that we are storing it in some variable that's called boot drive. We know that this is just a single byte. So what we need to do is we put into AX the value of the function that we need to call, which is 42H. And then we can just move into ESI the address of our LBA packet. This is pretty much the same thing that we did in our first stage. And once we do that, we should call the interrupt, which would be 13H. Should probably just write 13H, something like this. And just for 1 second, I'm just going to clear the carry flag so that we see what we have in it after the call to 13H, since it sets the carry if it fails basically. So here we do jump if not carry to I guess we can call it read OK. And otherwise we failed to read. So we need to do some other things here. But if we have succeeded reading the sectors that we wanted, we can just basically go to project mode and do something with the values that we've read. So if the read fails, we can do a number of things. Should probably just retry a number of times. So we can actually do something like compare. So we probably need some register that we haven't used. Should probably use BX or something. So compare BX to, let's give ourselves 3 retries. And we jump if lower or equal to some label that we call try again, something like that. This label try again would be probably somewhere here. Just do try again here. And of course we need to increment BX. So increment BX to basically go again. And if BX reaches 3, then we basically failed the read. So we should probably panic or something, but here not sure it's a good idea. So for now, let's just leave it at this. I'm pretty sure that we will never be in this case where we fail to read, since we are running on virtual machines. But for now, let's just keep it this way. And of course, should probably just XOR BX to zero it out before we start here. And yeah, that's fine. So here we go back to project mode, and here we know that we have used a temporary buffer. So we need to actually go ahead and copy the memory from the temporary buffer to the actual destination that we want to have. Right, so here we are going to move into ESI the address that we, we know what address that is, so we should just put into this, what did we call it? LBA buffer, I think. Yep. And here into EDI, we should put the destination into EDI, but I think EDI already has our destination, so we're not going to touch EDI. So what we're going to do, we need a counter in CX. So we are going to XOR ECX with itself. We are going to move into CX the actual number of
sectors
we've read. So where did we put those? I think that should already be in CX also, since we haven't modified CX anywhere. Yeah, that should already be in CX, so that's fine. Now what we need to do is we need to basically shift left CX or ECX by, so we want to multiply the number of sectors that we've read by the size of a sector to get the number of bytes. So we will do basically ECX times 512, except that we want to do the copy 4 bytes at a time, since we are in 32-bit mode. And that means that we are going to scale it down by 4. So we'll just shift it left by 7. There we go. That's pretty much sorted. And here we can just do rep nz, and here we can just use move string double, and this will copy EDI into ESI, or rather, sorry, ESI into EDI, as long as, and decrement CX as long as CX is not 0. And this also, so we need to just double check that we have our direction flag cleared. I'm not sure we did that though. So let's do it here. I have added clear, so CLD, clear direction flag, to basically ensure that when we do move string double, the ESI and EDI get incremented instead of decremented, which is what happens if the direction flag is set. So with this, I think we have at least a working prototype of what we wished to do. The only thing that we need here still is this boot dev. We need to figure out which disk we are booting from. And the way to do that is, so let's see here. We should probably go ahead and create boot dev. And this would be just a single byte. And let's initialize this to 80. And what we are going to need to do, since if you remember, we know that in our first sector here, when the BIOS loads us into memory, we know that in DL, yeah, there we go. In DL, we have the boot drive ID, and we've actually saved it here in the first sector. So to ensure that we get it on the second sector, what we need to do is we need to, so this here is where we jump to our second sector. So what I'm going to do here is just do, I'll just do something like this, move DL boot drive. There we go. And if we just go to boot drive, it's there, it's defined, so that's fine. So here we can basically just do this. Forgot something here. And with this, we can just go all the way up here, and just after this, and do move byte boot device and DL. That should be good. So now we have a few other few problems. We have moved the address of this label here, and that means that we need to do some adjustments on the rest of our linking, or at least the manual linking, since here the linker expects main to be at address PA0. So we need to basically check on which new address we are going to be and fix that. But at least we have something that we can consider as working as far as reading sectors go. And I guess we can just go ahead and remove these comments here, since we don't need them anymore. And we can just do some niceties like this. Like this. And that should be fine. Right, now that we have finished with the assembly side, we can just go ahead and copy the basically what we've just read into this page we've allocated, and probably copy it into this GPT header that we have here, or we can just remove this for now, because we still don't really need it. We can just go back to copying it once we need it. So for now, let's just remove that. What I will try to do though is see, or actually print a few things. So first thing I want to print is, so let's see what we have on this. Right, so we probably want to print these things here. Partition entries start, partition entries count, and probably the signature also. So let's do that. Right, so here we want to print the signature. So GPT, something like this. And the signature is 8 bytes. So we should probably just print it as a hex or a long hex with capital X. Just probably do something like sig equals that. And then we do partition start. This would be also a hex long or a long hex. Partition count, and this would be just a regular int, and yeah, that should be fine. That should be fine for now. So let's go ahead and do, this would be GPT, what was the first one? Signature. There you go. And then GPT partitions entries start, and then GPT partitions entries count. There we go. That looks good. So we just need to basically import or include console.h for printf. And with this, we should be pretty much done. So we just need to basically compile this a first time, look at where our main label is, and where our where our main label is, where our function this function here that we've created to read the sectors is, then we take those and we replace them in ASM helper, because we just need to put something here. Actually, let's change this to something so that it can build. And we'll put the basically the main address, the new main address here, so that it can be linked correctly with the rest of our C program. So let's do that and come back. Well, there we go. So a few bug fixes later, we can see that we now have, if I just zoom in a tiny bit, we now have our GPT, our partition table loaded in. We can see that the signature is correct because, so basically it spells EFE part. And we can see that the partition table starts at offset at sector 2, and that we have 128 of those. So what we need to do now is actually load the partition tables and go through them until we find a bootable partition. So I basically created a struct that describes the partition entry. And now let's go ahead and load the partition entry. So one thing I want everyone to notice here is that we are loading one sector starting from sector 1. And we know that the second sector is the start of the partition tables. And we also know that we don't really have 128 partitions. That's the maximum we can have, but we only have one of those. So if we go here and instead of loading one sector, we load the full page, which is 8 sectors, we should, in theory, should have already read the partition entry table. So we don't really need to go back to disk again for that. So let's do this. Great. So let's create partition entries. Start. This would be just GPT partition entries start. And what we will do is we will create a pointer to partition entry, and this partition entry, and this pointer will be so partition entry pointer, and here we are going to take the address of GPT, so something like this, probably even course it to U32 so we don't have any warnings, and we will add to that a arc page size. No, not arc page size. We should add to that a sector size multiplied by so sector size. I guess we don't have this, so we need to define it somewhere. Multiplied by so partition entries start, basically. Let's define that. So define sector size, and this would be just 512. There we go. Yeah, and we should also just force the conversion of this to U32. Right, so what's the issue here? Right, so let's just rename this to entry, and that solves it. Okay, so now we have our entry. So what we need to do is we need to basically loop over the entries that we have all the way until we reach the number of entries, basically. So that's GPT partition count. There we go. Right, so now we need to find the exact entry type that we are looking for. And to do that, we will compare two things. So first of all, we need to find a partition of type EFI system, I think, or we need to find a partition that's marked as bootable through the attributes. So let's go ahead and do that. So entry. So if, first of all, let's get rid of everything that's that we don't really need. So if type is 0, basically, and I'll just check the first byte. If it's 0, then and entry so start LBA is 0. So these kind of entries are unused, so we should just ignore them. So we go ahead and continue. Oh yeah, okay. There we go. Right, so now if the entry attribute, so if we take just the second bit of the attributes flag, so bit 2 of this partition entry basically means that this partition contains files that are needed to load or start an operating system. So it can also be used to indicate that this partition is basically a bootable partition. So to do this, we are just going to end it with 2, since 2 in binary is 1, 0. That basically ends it and just takes the second bit number 1, index and starting from 0. So if we have this, or we need to compare the type, so entry type, we need to compare it to some predefined list of GUIDs, and we need to basically pretty much just implement a new function that will do strncmp, and we'll give it the type, we'll give it the GUID, and we'll give it the size. We know that it's 16. Yep, it's 16. So we'll do that. And if this matches, then we basically just break. Otherwise, we need to basically increment our entry. All right, just 2 pluses. And with that, we should have the entry to read our partition from in entry. So let's print. Let's first do a check. Let's check that entry. So if entry is null, right? We basically just print f something that says, I should probably do something that basically I should probably create a or a few helpers for login to basically add the log level. So error could not find a valid boot partition. Something like this. And here we just basically spin something like this. Otherwise, we basically have our partition, so we can just print some info about it. So let's print, for example, found EFI partition. I guess we should add LBA. Yeah, we could just take it as a number, and that would be entry start LBA. Yeah, that's good. So let's first create this EFI GUID. So if we go back to this Wikipedia page here, we can see that we have the GUID for the EFI system partition. And we can also just, we could use also XXD to take a look at what we have on our disk image. And here we can see that we have, we actually have this, and this is the, and this is the GUID for our first entry here. So if we just copy this and go ahead and create a variable, should probably just create somewhere here. And it'll be just a U8, call it UFI GUID, and we know it'll be 16 bytes, and we'll just initialize it in place. And now we have our GUID that we need to compare to. So we just need to implement this stir and compare function, and we should probably just pre-include string, string.h. And if we go to string.h, we can go ahead and define a function that's stir and comp. Right, so from the manual, we can see that stir and comp takes basically two char strings and the size, and it returns 0 if they are equal up to that size, and it returns negative if S1 is less than S2, and positive if S1 is greater than S2. This would return an int. This would be our this, and here we're gonna take so two const I8 pointers, call them S1 and S2, and we'll take a U32 n. Okay, and we next go to this here, U32 stir and comp, and here we go. Right, so what we need to do here is loop through the whole strings. So while I is less than n, we just increment I and go our merry way. So what we need to do here is check that S1 at position I is different from S2 at position I. If this happens, we need to check basically if S1 is bigger or smaller than S2, or rather S1 of I is bigger or smaller than S2, and that's what we are going to return. If S1 is to be the larger one, we return a positive value, otherwise we return a negative value. So what we are going to return here is basically S1 of I minus S2 of I. And of course we need to just course these to be U32s. There we go. To avoid warnings. Otherwise, if we get to the end and the strings are a match, we return 0. So now if we go back to file system here, the strncmp, we want them to be a match. So we should do something like this. Actually, we can actually just go here and change this to, that should be fine. Should be fine. We can just tell it that it's an I8. It's const I8 pointer. And this, of course, needs to be const. Yeah, we can just create it as an I8. Should be fine. Okay, so let's save this. Let's give it a compile and see what we have. So we don't have any new warnings. That's cool. Let's see what we have here. Okay, so we have a partition. The LBA looks a bit dodgy, so let's see what we actually have. So for reference, this partition here starts at LBA, so 0x800. So that's what we are expecting to see. Okay, so let's see here. Okay, I think I see what the issue is. This start LBA here is a U64. So we should probably change this to reflect that. So we currently, the only thing that can be printed as U64 are long hex. So let's use that and see what we have. So let's rebuild it quickly and see what we get. If we zoom in a bit, no, it's still a bunch of zeros, so it's not good. Oh, hold on a minute. So there might be a slight issue here. We are basically reading from the disk. We are reading from disk from sector 1. So we should probably take the offset from this partition entries start. And that should solve our problem, hopefully. And it looks like it did. So now we are actually pointing at the correct partition. We know that it's an EFI partition. So the next step will be to read the partition, take a look at what kind of file system it has on it, and read the files from the file system. It was a long one, but we needed to do this. The plan for this bootloader is to be reusable. So the first step to have that is to be able to use a config file to describe where the kernel lives. And of course, the first step to using a config file is loading it from disk. That's why we are going to go through this, read the partition table, find the boot partition, read the file system, write functions to traverse the file tree and find our config file, read the path of the kernel, and then do it again, traverse the file tree to load the kernel into memory and do everything that needs to be done to execute it and run it. That's it for today. If you like the content, hit like, subscribe, and I'll see ya. Bye.